What mechanism? What step of the mechanism? Thank you. Slow step agrees with rate law. Okay, so we're going to talk about what those mean more specifically here. But I hope that connects a little bit with what you're doing. I'm going to show you an example from the NSMI before I start talking a whole lot about this, because I think the example really will kind of make things more clear. So here's our proposed balance. Here is our balanced chemical equation for a reaction. The experimentally determined rate law is K concentration of NO2 to the first power and F2 to the first power. So we're saying they're both first order, yes? Okay. According to this person's idea, they think the mechanism of this entire reaction here, they think this reaction here occurs by these two steps, step 1 and step 2. So they're saying nitrogen dioxide combines or collides with fluorine gas to make this thing in a single fluorine radical. They say that's the slow step. And then they say the fluorine radical combines again with nitrogen dioxide to make NO2F. Okay? And then they said, is this mechanism viable? So what you would do is just add up this reaction. So notice on this reaction, NO2 and NO2 are both on the reactant side, so you'll notice they do not cancel, they actually combine. So those two come together to make two NO2s. What about the fluorines? Or actually, let me stop there. This fluorine here will cancel with this fluorine here because they're the same they're on opposite sides of the yield symbol. So they actually will cancel because they negate each other. Is there anything else that negates each other?
NO2.
Not quite. This was, you can't really see that too, I just covered it up. But this one's on the, but they're both on the product side, so they actually sum together. So it makes two of them. So this F2 stays, and two NO2Fs are made. Okay, so does this reaction match the BCE original? Yes, so first criteria is an agreement. The sum of the BCEs of the steps match the BCE proposed. And then your next step is to say, does the rate law agree with the slow step? So from the slow step, you pull the molecularity. This is the only time you're ever allowed to pull the coefficients and make them exponents. It's because it's an elementary step, it's a single step. So there's a 1 here and a 1 here. Does that relate to the 1 here and the 1 here? Yes. So you would say the slow step, which is the rate determining step, does determine the rate as a first order, according to the reactants proposed. So then, because both criteria are satisfied, you would say this is a viable mechanism. That's it. There's some more terminology. It's like we're going to talk about intermediates, catalysts, and stuff like that right here. Write down what you need to. If you print out the packet, you might just add to it. I'll let you guys read that first, and I'll tell you how to identify.
What page is this?
Someplace between 20 and 23. I will find it. You guys read write down what you need from the read book. These are simple definitions. I will ask them on multiple choice. Please don't get them wrong. These are definitions. I hope that will make sense once you get there. Let's just see them. It's on page 22 in the packet, but it's not very explicit. So you can probably assume that an intermediate is something that is in between two reactions, and so they will always be formed. So it's a species that's formed early and then immediately consumed in the next step. So does it fully exist at the very end? No, it gets canceled because it's going to be formed as a product in step 1 and then used as a reactant in step 2, so they are on opposite sides of the yield symbol, so they cancel. Intermediates are always canceled. They're not going to be in the full BCE. Related to that is a catalyst, but it's related actually in an opposite way. I'm going to look down here. A catalyst is going to be a reactant in the beginning, and then later on appears a product. Does it stay in the BCE overall? It doesn't, because so it's going to be a reactant early, and then a product later. And so when it's on the reactant side and the product side, if there's one on each side of the yield symbol, they will cancel each other out. But that's truly the definition of a catalyst. In your previous life, what was your way of describing a catalyst? It speeds up a chemical reaction, it lowers the activation energy, and does it get consumed in the reaction? No, it does not get consumed. So the reason this is related is because it's not consumed, because it is present as a reactant, and then you can see it's present again as a product, but it's because it never changed. That's why it's there from beginning to end, and it's not intermediate and consumed. The really most important one here is the RDS, rate determining step. Rate determining step is the slow step, and that's the one that makes sense. So in your kinetics all screwed up lab, who was your rate determining step? Who? Shannon? Shannon was fast. I thought it was Lewis. 90-second one. That was after the all screwed up part was all screwed up. So I think of this as a relay team. I would be your slowest step. Okay? If you're passing the baton on, the slowest runner is going to determine the overall rate of the how fast your team's going, right? So like swimming, you guys do the 50 meters, right? Medley. Here's your slowest step. Is it Lewis? Okay. So you can see that like this makes sense. Whichever one is the slowest is going to be the one that is the rate law. But that's the only time, once you have the elementary step determined, that's the only time you're allowed to use the molecularity, aka the BC coefficients, and that's when you can pull the coefficients as orders. Okay, so that's when the molecularity will determine the order, only when they're written out in step form. Okay, I'm gonna show you guys some more examples of this, and if I need to come back to definitions page, I will, because I'm going to use these terms more readily now. These are the two criteria that we just wrote down. If you want to just jot down two criteria and say what we just said earlier, sum of elementary steps equal VCE, and then RDS coefficients match rate law. That's about as simplified as I can make it. So RDS coefficients, copy, equal rate orders. And that's something you will explain on an FRQ. It'll say, how did you know this rate mechanism or this proposed mechanism was viable? You would explain this. And if you don't say the word molecularity, you don't get all your points. Okay, so make sure you're using the terms because they're there for a reason. And it kind of gives you the advantage of understanding a more in-depth layer of chemistry. So whenever we say molecularity, we mean coefficients. And then make sure you say, if you want to write RDS, just define that term first in AP exam. For me, I'm good, I get it. Stuff down here gives us some information about what are types of mechanisms that could occur or how many things have to collide. There's very rare ones and there's very common ones. Things that are rare are things that actually require three things coming together. So termolecular means three molecules coming together. So then you can assume what the other ones mean.
One molecule.
Right, two molecules, and then one molecule just simply doing what? Decomposing? Yeah, right. So this would be more of a decomposition reaction where one molecule itself separates, so it's decomposing. This requires two molecules, and it's most common because it's really easy for two molecules to collide, but they have to collide with the correct orientation for the reaction to actually occur for it to be an effective collision. This one requires three molecules to collide. That's like somebody throwing three basketballs up at the same time and hitting exactly in the right spot, exactly at the right time with the right amount of energy. Is that really going to happen? Not as much. Those are pretty rare. This one's not so bad. Good here? Okay, a lot of information up front, and then we're going to start some mechanisms. This is on your sheet on page 14. Oh, right. Yeah, okay. 14. So if you want to write on your sheet, that's totally fine. So you tell me, is this mechanism viable? And, oh, sorry, actually, let's answer the questions I have here. I'm saying that this mechanism is viable, but we're going to confirm. First of all, what step is the rate determining step? Give me a guess. Step 1 or step 2 based off the data given?
Step 1.
Why?
Because the reaction NO2 is in the first one would be the order.
So what is the order in the rate law?
The order is the slowest step.
Oh, the order is a 2, right?
Yeah.
So what are you comparing that to in step 1?
So 2.
The 2 NO2s, right. So you're like, okay, step 1 is the rate determining step because the second order nature of NO2 from the first BC having 2 NO2s in it. So the molecularity matches the rate law. Molecularity matches the rate law. All right, are there any intermediates?
Yeah.
Which ones?
Nitrogen trioxide.
Nitrogen trioxide, because you can see it formed, and then what? Immediately consumed. Okay, so nitrogen trioxide is an intermediate. So nitrogen trioxide gets canceled out when we're adding up our BCs, because an intermediate does not exist for long. Are there any catalysts? So definite, right, nitrogen dioxide. How do you know that? Because, but specifically, where does it start and where does it end?
It's consumed earlier.
It's not consumed, actually. It actually looks like it's consumed, but it's actually still there. So it's present. How about we say it's present at the beginning of the reaction, at the end, and at the end of the reaction? That kind of lies along the definition of a catalyst. So it's present early, and it's also present later, meaning it was not consumed. It's not like it was reproduced. Let me tell you, it's still there. So NO2 would be our catalyst, and that actually will not be present in the reaction, because is it a part of the reaction? No, because a reaction is a rearrangement of atoms from reactants to products. Catalysts are not rearranged, they're simply there. And so probably what's happening is nitrogen, one of the nitrogen dioxides is maybe serving as a catalyst, one of them is a reactant, and that's why there's 2 of them there, to show the correlation of where oxygens are going and so forth. So then how would you verify for sure, though, that we've already done like the rate criteria? What other criteria do we need to verify? We looked at the rate determining step, we looked at the molecularity, we've confirmed that. So does it match the BCE?
Yes.
Yes, NO2 plus CO yields NO plus CO2, and that's what that says. So that's how you verify 2 criteria. Let's keep going. This, oh, draw yourself this, sketch this. You'll see a graph like this. They had one on the first year I was teaching AP Chem, and I never showed my students a double humped little reaction coordinate, and they're like, what is this nonsense? So I want you to be familiar with multiple types of graphs so that you're not scared and then whimper and cry when you exam. It's going to happen anyway. When I pack your goodie bags, I'll put tissues in there. Okay. Well, I'll give you goodie bags, that's it. Okay, so this one right here, you can tell has how many steps in its mechanism? 2 steps in its mechanism. A single-step mechanism would have 1 hump. A 4-step mechanism would have 4 humps, right? So you can see that this first step has a huge activation energy. And what would this be right here? What would you call that? Using your vocabulary we just learned. So we went from reactants to products, but what is that specific one called? Right, that is the intermediate. Because that's the intermediate that's produced in step 1 and consumed in step 2. Yeah, you see it? Pictures to words, right? So the first step has a really high activation energy. The second step has a pretty small of activation energy. Why is the first step the rate determining step? Because it's slower, because it requires the most energy to achieve that transition state so that it will form the intermediate and then so forth. So because step 1 has a higher activation step or activation energy, that makes it the rate determining step. Okay? And then if I knew the reactants, I could actually write out, so like if this was chlorine plus oxygen, I would see those coefficients of 1 and 1, and I would write the rate order, the rate law as what? Rate equals K times
the concentration of CO2.
Cl2 first and then O2 to the first. So that's me showing you, like, I could give you reactants, and once you've identified it as the rate determining step, you would use those coefficients to make the order. Okay? This is a second example on y'all's. So tell me, if knowing all this information, is it a possible mechanism? Tell me really quickly your two criteria. Did we just do this one?
Yeah.
My bad. Sorry, I had one that repeated. This was the one I'm looking for. Okay, tell me quickly catalyst.
NO.
So nitrogen monoxide, because it's present in the beginning and the end. Intermediate. Nitrogen dioxide is the intermediate. Okay, so what's the full reaction? Okay, what reaction is this? Ozone reacting with a free radical. This is a free radical. And it actually does create oxygen gas in our atmosphere. That's good. That is a good reaction. We do like that to see that occur. Sometimes it forms other free radicals which would harm our bodies. We were talking about antioxidants. Okay, so that's oxygen. Free radical is a really, really, really good oxidant, right? Because it's oxygen, it's a really great oxidant. When it gets inside your body, it oxidizes your cells, it destroys your cells. So then when you, right, because it's going to be very easily taking electrons. Yes. So then you eat antioxidants to combat any of those free radicals you come into contact, because we're in contact with them all the time. Where would you get your antioxidants? Blueberries, and what else? Bananas. Usually dark pigmented fruits. Blackberries, apples, pomegranates, potatoes, I'm sure. Okay. All right, so let's do this one for me. Tell me the rate law. Tell me the rate law. Rate equals
K, concentration, C4H9Br.
H9Br, done. Right, to the first power, because there's a one coefficient up there. So the one coefficient, though, is the what of that reaction? The what of the reaction? Correct term. Molecularity of the reaction to make the order match. So basically, I always want you to say the molecularity of the reaction matches the order of the rate law. Molecularity matches order. That's a good phrase. It's a single phrase for it. I'm going to stop on that one because I think you guys are getting this. There's this one that we have to do. This is a special one. Okay. So between the two mechanisms proposed, is this one on your paper? It gives you two mechanisms.
Yeah.
Okay. So given this reaction, given the rate law and the two mechanisms, which one is viable, or which is most likely the reaction?
Number 5.
I believe it's like an extra, and I can't show the whole thing. All right, so mine's teeny, but I can see the whole thing now. So you guys look at it, do your criteria, do it on your paper, and then tell me what you think. All right, so tell me what you know about the first one, the first proposed mechanism. All right, so are the two criteria met?
Yes.
Yes, both good. And I'm assuming that you guys can cancel things out, look at the slow step, look at the molecularity, and then say that great phrase.
Molecularity matches the order.
Right, the molecularity of this reaction matches the order of the rate. Second step, tell me about the criteria. Yeah, question.
The molecularity of H2 doesn't match.
Right here, yeah, on this, because if you're looking at the slow step, if you're looking at the first mechanism still, you might be able to take one. Sorry, I'm on the first mechanism here, 2 and 1.
Right.
Okay, looking at the second mechanism, tell me what you guys know.
The sum matches.
All right, so you said the sum matches, and tell me how you got that sum.
canceling stuff.
Just canceling stuff, specifically stuff.
N2O2
Okay.
twice. And then again on the next step.
N2O.
Oh.
And so then you get 2NO plus 2H2
Goes to
yields,
N2 plus 2H2O.
oops, N2 plus 2H2O. All right, so what do you know about this one?
The molecularity doesn't match.
Hold on, stop. What are you supposed to be comparing this to? What are you comparing this to? The what? This? No, not to the elementary stuff. To the BCE proposed, right? Which I can't show because it's like right here. Does our BCE match the proposed BCE?
Yes.
Yes. So you just told me the sum of the steps equals the BCE proposed. Criteria 1 met. Criteria 2. No. Why? Tell me why you said that at first.
Because
And then I'm going to change your mind. What does that rate law say?
that rate loss, there's the rate should equal K times the concentration of N2O2, with an order of 1, times the concentration of H2.
Okay. What, in this case, in this reaction mechanism, what does N2O2 equal? 2 NOs. Do you see the rapid equilibrium in the first step? This double-headed arrow means rapid equilibrium. It happens so fast, basically, this NO2 here is going to just quickly collide and make N2O2, and then N2O2 is quickly going to collide with hydrogen gas to make the products in the second mechanism step here, right? So, but this is so transient, this N2O2 intermediate, it's there for a split second before it collides with the hydrogen gas. We basically say that these two things are equivalent because this is not there very long, nor is this there very long. So we actually can do an interchange because N2O2 equals 2NO, this can be 2NO. Now does it match the rate law? Yes, and so you would explain that by saying the rapid equilibrium in step 1 occurs so quickly, the N2O2 are, the 2NOs are basically going to be, I'm going to say basically colliding with H2, but then what kind of reaction would that be? Unimolecular, bimolecular, trimolecular? Tri, and then what do we say about that? It's very rare. So this would not have a high level of efficiency if it was just simply N2O2 and that colliding with hydrogen gas, because that's a trimolecular reaction. So we say that there's a fast equilibrium that occurs first to combine the NOs so that in the end, it's actually in the middle, but in the end, it's what kind of reaction? Bimolecular. But that is still, you can still manipulate that, those elementary steps to prove that the rate law does agree. So both of them are viable, but which is more likely? Why? Why?
Because 2NO already reacts with H2, it's more likely to happen with the H2.
No? Tell me what kind of reaction that one is. Uni, bi, or tri? That's 2 molecules plus 1 is 3, right? So this one's like, hey, I have no choice. I'm a trimolecular reaction. This one's like, I found a shortcut. Let's collide these two babies together, make N2O2, and then have that collide with hydrogen gas. Is that one more likely or that one more likely? Second one. Only because we allow for two things to come together first, so they singly will react or collide with hydrogen gas. So this is actually the more likely one, simply because of that manipulation of the molecularity of it. Okay? So that's a little harder. That's more of AP style. So on your packets, I'm going to have you guys start this for a minute. On your packets, it says reaction mechanism worksheet. It should be right next after these notes. Mechanism practice worksheet, 15 and 16. Take 10 minutes right now, get started on that. You probably get through question 6 at least, or more. Some of these are quite easy, okay? Work together on this as needed. And I'm going to talk about Arrhenius for 10 minutes at the end of class. Arrhenius' equation.
These slides on these documents.
Excuse me?
These slides, these documents.
Website? Yeah, and I'm going to talk, I have a couple more things to talk about actually before I can talk about Arrhenius. So you guys do your worksheet right now. You can write on that worksheet if you have space. It actually makes it a little time saving.